We wait a minute before we start for having everybody joining. Welcome. Okay, I think we're ready to start. So welcome everyone to the 2022 SRO Geophysics Virtual Open House Info Session. My name is Alice Gabriel. I'm Associate Professor at Scripps at IGPP, and I'm the coordinator of this virtual open house. And we have a packed agenda for all of you that is on the slide here. So we start with an introduction of the Institute of Geophysics and Planetary Physics by our director, Dr. Peter Shearer, who will take it over from me in a bit. Just a couple of notes before we start. Please stay muted during these pitch talks and presentations. We have a Q&A session at the end, but feel free to post questions in the chat while we're going through this material. And also this is recorded and will be posted on YouTube. So anybody that's not here can look at this asynchronously. And if you have further questions that may contain your personal information, please email to gp-admission@ucsd.edu. And with this, I'll let Peter Shearer take over the introduction to our institute.
Okay, well, thanks for coming. Although I've only been the director of IGPP for a few months, I have been here much longer. I first came as a grad student in 1981. So let me share my screen and put it in presentation mode. So you might wonder why this is a geophysics open house. Why am I presenting this? Well, IGPP, at least at Scripps, has most, although not all, of geophysics that we do. And it's located, as you can see here in the yellow box. It's part of the Scripps Institution of Oceanography, which is this larger campus. And that in turn is part of the University of California, and the main UCSD campus is on the knoll up the hill. And I'm trying to advance the slide, and there we go. Okay, so first of all, location. We're right on the beach. We really have a beautiful building and location. We're also in San Diego, which is modestly called America's finest city, but at least in terms of climate, I think that's true. You'll hear a little more about that from the student when you hear the student talk. Our physical grounds are really beautiful. The building that we share, and I think this helps to foster a sense of community. We all enjoy our work environment. This is an old photograph of our conference room where a lot of the classes are taught. This was way back in 1966, and it looks like somebody's explaining seafloor spreading, which was, of course, a new concept at the time, and one that Scripps was really involved in historically, the development of plate tectonics. One of the advantages of IGPP in geophysics is that we're quite large. There's over 20 faculty that span a wide range of disciplines, and there's strengths in both theory and modeling and observations. And what this means is that you're not limited to the projects that you might have thought you were going to work on when you first come, or those that your advisor is involved in. There's really a broad spectrum of things that you would be able to work on. There's also the advantage, there's a lot of expertise that might be just down the hall that'll be able to help you with your research. But I did want to focus on the science and to brag a little bit about it, I guess. Some examples of things that have been done at IGPP. We're really pioneers in instrument design and data collection. I mean, not just using data, but also generating new data sets. There's a long tradition at IGPP of theoretical rigor in developing new techniques. I just wanted to highlight a few examples, and there's so many to choose from. I thought it'd be fun to just show examples of the science articles that have been published. And even when one limits it to that, there's a lot of examples, but this is one you may hear more about from Helen Fricker, the use of satellite altimetry data to discover these subsurface lakes under Antarctica. Another example is from Dave Sanwell. This is using remote sensing data to map the surface of the ocean, which in turn is related to structures below the seafloor, and they were able to discover many new features on the seafloor. And a more recent example was the discovery that many large earthquakes actually trigger dynamically early aftershocks that are buried in the main shock coda, so they're not that easy to observe. But Wenyan Fan was able to show that globally these events are more common than was previously thought. I decided, however, not to completely limit myself to science articles, because I wanted to have an example of a more theoretical study. This is a very well-cited work from Steve Constable and colleagues here that developed a very practical inversion scheme for electromagnetic data that solves some of the non-uniqueness issues that had plagued such inversions in the past. I did, however, want to say a little bit about what is going on at, in fact, the entire University of California system right now. This started on Monday, and you may have read about it. So there's a strike that involves the graduate students and the postdocs, among a few others. I think personally, for myself and almost everybody I talk to, I hope that this will be resolved soon. It will result in increased pay and benefits for graduate students and postdocs. But in any case, I'm sure the strike will be resolved by next fall, when you would be coming. If you want to learn more about the strike, both from the union point of view and the university point of view, there's some links there. And that's all I had to say.
Thanks a lot, Peter. Our next speaker is Matti Morsfeld, who is the Geophysics Curricular Group Coordinator, and he will introduce you to the details of the GP program at Scripps.
Okay, yes. There might be some repetition, but I will give you a few more details. So you've already seen from Peter's slides our beautiful building. And I also wanted to give you a little bit of an overview of how we are placed within the larger Scripps Institution of Oceanography structure. So there is, this institution is organized in 3 groups, one about climate science, physical oceanography, applied ocean science, then there's a biological section, and then there's geosciences, and we are within this geosciences of the Earth, oceans, and planets section. Within this curricular, within this bigger group, there's also 3 subgroups that you can also interact with when you are here. So just because you would apply to us doesn't mean that you cannot be interacting with all the other groups that are here. There's also common features across the entire program. You will get a 3-person guidance committee for your first year. I will explain that in a little bit more. There's a departmental exam at the end of the first year that should not scare you. It is written and oral, and it is a thing you will just do. We all encourage that you begin research as soon as possible, although the first year is typically a little bit class heavy, and I will get into more details about this also in a little bit. And with these 3 sections, there's 3 degrees you can earn, but if you come to us, you will have a degree in earth science. That would be the ultimate goal. Also, since we're an oceanographic institution, we have boats or ships that I'm not really qualified to talk about. You should ask somebody else about these, because I'm on the theory side and I do not usually spend time on these vessels. But I do know our curriculum very well, and we have a philosophy that we give you a pretty structured curriculum that offers a lot of classes, and you will see a list of the classes soon. We'll give you access to a broad range of specialized and interdisciplinary courses. You can take courses until your 5th year if you like. There's enough courses you can take. You can also stop taking courses very early on. And as Peter already said, Scripps itself is very big, so there's probably something to do for everyone. And we want you to find an exciting research project as soon as possible, and that you have fun doing it and completing it. And when you're here, of course, we also encourage you to take advantage of the field and or seagoing projects, and also computational resources that we have, which I use a lot. Now, to get you a little bit into what the program actually looks like, especially in the first year, there are foundational courses that we very strongly recommend everybody takes. There's a data analysis course taught by me, a second data analysis course taught by my colleague Duncan Agnew. There's physics of earth materials, and there is geodynamics. And then we also have a 3-quarter series called Geophysical Research Skills, which I think is unique, maybe not in the world, but it is pretty special, let's put it this way. And in this sequence of courses, we teach you skills that are traditionally not taught. So we talk explicitly and teach explicitly how to write scientific papers or articles, how to make good figures, how to give presentations, and also how to synthesize the geophysical literature. That's part of this research skills series. And I think this sums up the philosophy pretty well. We want to give you a broad foundational geophysical knowledge and equip you with all the other things that you need to be a successful researcher throughout your career. Here's a snapshot of the list of classes that we offer. So you can see that it's a long list. You can look at it more. I think all the slides will be made available, and you can pause the YouTube video and see what's being offered. So they're all offered very regularly, and you have a lot of time to take any subset of these courses that you may be interested in. Here's roughly a timeline. So in year 1, you focus on classes, and you will pass the departmental exam at the end of your first year. Then in year 2, you may still take a few classes, but you lean a little bit more towards the research. Year 3 is a qualifying exam where you propose a thesis outline and discuss that with a committee of 5 people. And then you are basically a full-time researcher until you defend, which on average happens after 5.74 years. We also have a support system set up. So that's the departmental and guidance committee that came up earlier. So there's me, that's a photo of me when I was little. And there's I'm the curricular group coordinator, and we have a curricular group advisor, that's Dave May. He will meet very soon. And there's a departmental committee, which consists of 3 people, and they will meet with you at least once a quarter. They help you with choosing which classes to take and when. And they are a generally useful resource for all things first-year grad school related issues. So any conflicts that you have or any issues that you have, typically the departmental committee and these 2 people will be there to help you. The evil side of that committee is that they also compose the departmental exam. But as I said, you should not be worried about that exam, but that's also part of their job. And then, so everybody gets the same departmental committee, and then together with the advisor that you are choosing in your first year, these 4 people will be your guidance committee. for the first year. There's another large group of people that you would typically encounter on a day-to-day basis. So there would be me and Dave May as curricular group coordinators and advisors. The departmental committee, you already met Peter, he's the director. There's people that take care of the buildings, you will see them all the time. There is great support for computers, you will interact with them quite a bit. Of course, you talk to your advisor, all the instructors of your foundational classes. There's a relatively large group of students who all interact and have fun together. So you will, of course, be around them. And then you have the cohort of the 23 year. The last thing I wanted to say is, besides the great science, we also have some fun. So again, this is where we are. So the first year office is here in this little room that hangs over the cliff. It's called the Keller. Many of your classes will be taught over here. And then the faculty and your offices or other student offices are east of what you see here. And then we have a lot of activities. So on Tuesdays, every Tuesday, we have a seminar. On Monday morning, we meet for coffee. On Wednesday afternoon, we meet for tea. And on Fridays, more or less every Friday, there's a happy hour that brings together all of SIO. So that's every Friday, that's a pretty big gathering. And also you can suggest courses. So if you find 4 or more students in one faculty willing to talk about a certain topic, you can suggest a course, and that can be done. And also there is a movie about IGPP, which you may want to watch. It's called Bag IGPP. And that movie is a little bit old, but it is there. And that's all I had prepared. So I'm going to hand it over to the next person.
Thank you, Matti. You wanted to say historic, not old, I think. Okay. Our next agenda point is introduction to the geophysics student experience. And this is given by Alice Raffer, who's a third-year grad student with us, and he's the student representative. And due to the ongoing strike that Peter mentioned, and that the faculty is supportive of, he pre-recorded his talk, and I will play it for you now. Sorry, one more time with the optimization for the video. Yes. Okay.
Hi, everybody. My name's Ellis Favre, and I'm a third-year PhD student at IGPP and Scripps, and I represent the geophysics program on the Scripps Graduate Student Council. And I was asked to speak a little bit about student life at IGPP and Scripps. I wish I could be there to discuss with you all live, but as you may know, graduate students, postdocs, and others are currently on strike across the entire UC system, over 48,000 individuals. And this is driven primarily by the fact that cost of living in California, and in particular housing, has skyrocketed over the last few years, and academic workers' pay has not consequently reflected this. So currently the unions which represent these groups are negotiating with the University of California over issues of fair pay and other rights and benefits, which are really essential to fostering an equitable academic environment, as well as just living comfortably and securely in California. And so while it may seem discouraging that issues measures as drastic as striking are taken, and obviously this is driven by very substantial issues, it's a really significant and important moment that all of these groups have been able to come together and reach unity and organization to really fight hard for these benefits for both current graduate students and future graduate students. And historically, academic workers' strikes have resulted in significant gains for grad students. And so there's a lot of high morale and optimism associated with the ongoing strike, because it's very likely that we'll be able to win substantial gains for everybody. And so, just know that this strike reflects the fact that there's a lot of people working really hard to try to improve the financial security and overall working conditions for in particular graduate students at UC San Diego and all UCs. So I will talk also about grad student life at Scripps. There's about 300 or so total graduate students across all the curricular groups, with about 50 or so being in IGPP. And there's a lot that goes on a daily or weekly basis in the department. During your first year in particular, you'll be all working together down in the basement office with probably the best view of any office at Scripps or any office in California in general. And you'll be taking similar classes during your first year, including a series of first year seminars where you'll practice academic skills like writing papers and proposals, and presenting and making slides and abstracts and figures. On a weekly basis, there's a number of things that go on around the department, like Monday morning coffee and the weekly department seminar, as well as tea time on Wednesday afternoons. And then there's also a variety of student events that happen on a regular basis, like Sci Chat, which is a student seminar. There's sort of miscellaneous student events on about a monthly basis, as well as the geophysics student camping trip, which we're planning on doing for the first time since COVID started later this year. And of course, there's a wide variety of stuff going on at Scripps at large. There's the peer mentor program where you'll be paired during your first year with a senior student to help you learn the ropes and get settled in at Scripps. There's events put on by the Grad Student Council, as well as many other seminars besides the IGPP seminar. There's the Scripps Student Symposium, which happens each fall at the beginning of each fall quarter, where you can go and see student presentations and posters and learn more about the research that's going on at Scripps. And of course, there's the biggest social event that happens on a regular basis, which is TG. And it's a sort of weekly-ish happy hour on Fridays that happens on the Surfside Lounge, which is the student space on campus. And there's a number of different affinity groups that you can get involved in, including women and minorities in science, as well as queer at Scripps. And so there's a lot of opportunities to get to know other students and other people at Scripps outside of just IGPP. And so a little bit about living in San Diego. Here are a few neighborhoods where people live in, sort of in order of how popular they are. University City, or UTC, is closest to campus, while neighborhoods further away near downtown have a little bit more of like a city feel and more going on kind of outside of academic life. And it's also recommended too that you check out the grad student housing apartments, including the Coast apartments, and get on the wait list as soon as you can, since the wait can be quite long. Something to note too is that there's a new trolley line which connects to UCSD to downtown directly, which opens up some additional housing and commuting options. And so, of course, outside of academic life, there's a lot going on in San Diego. Geophysics students enjoy all sorts of outdoor activities like surfing and climbing, as well as a lot of people are getting together to watch movies and cook and do games, in the evenings or weekends. And of course, it's all true what you hear about San Diego. The weather's great. There's so many beaches, and there's a great range of foods from all sorts of different cuisines, as well as a really big craft beer and craft beverage scene. And of course, San Diego is close to many, notable locations in Southern California and the Southwestern US. And so I hope this was useful information for everybody. If you have any questions, feel free to send me an email and we can chat offline. And I would really lastly, again, encourage everyone to learn more about the strike that's going on. It's a really important event and will definitely be affecting the student experience at UCSD and all UCs in a positive way moving forward.
So thanks, Alice, for taking the time to recording that. And now we enter a series of short pitch talks of the different research teams and groups that you can interact with at IGPP. And as Peter pointed out, you really can take advantage of that large faculty body we have and the diverse research teams you can learn about. And our first speaker is Wen-Yuan Fan, who will talk about seismology.
Great, thanks, Alice, and welcome everyone. I got the honor to introduce the IGPP Seismology Group. We have a pretty big research group here, including myself, Professor Gabi Lasky, Professor Peter Scher, Alice Gabriel, your faculty Jennifer Hayes, Ross Bernard-Turner, and Ron Miller. These are the current faculty are actively engaging with students and potentially offering advising opportunities. And we work together pretty closely, and we also have a pretty big seismology group meeting every Friday for this quarter. So in addition to this group, we also have a lot more faculty who members who also work on seismological related topics. And some of them are recently retired, but still very active in research. And some are from other disciplines. You will learn a little bit more, but also work on earthquake and seismology related topics. So a quick short description of what we do here is that we really try to understand the Earth and seismic sources from multiple using multiple ways, including developing series and doing numerical simulations, design instruments, and do field experiments, and also process large different data sets. So if you're interested in any of the people listed here, even beyond, please feel free to reach out to us and talk about your interests of potential future projects if you do come here. And that's all I have for seismology. Thank you.
Thank you, Wen-Yuan. We move on to Earth Interior and Geodynamics, which will be presented by Gabi Lasky.
Better unmute myself here, so welcome everybody. So I'm supposed to talk a little bit of the elevator pitch about the deep Earth research, and that actually spans several disciplines within IGPP. And so, this is an example where, you're not gonna be isolated in a disciplinary bubble or so. So in this case, we have folks from seismology and electromagnetism or geomagnetism, but also computational folks and geodynamics work together to solve or answer questions how the deep interior works. And you've seen some of these pictures of the faculty already multiple times, and you will again. But it's really, all the students that we have and also the postdocs that we have that provide, tremendous amounts of research in that area that we could otherwise not do. So this is a little busy here, but I think I want to stress at this point that we do all three kinds of research. So observational, so we collect data, we actually assemble maybe even standard data sets, certainly standard models that then are used by others, even outside of IGPP. We also develop theoretical tools or do theoretical research, come up with new algorithms or involving HPC, high performance computing. And as previous speakers already mentioned, we also have a variety of facilities For example, an ocean bottom instrument pool, seismometer pool, but also electromagnetic, magnetotelluric, marine, actually. And then we have a group that conducts part of the Global Seismic Network, the IDA group. And we have a interdisciplinary observatory, the Pinion Flat Observatory, where we do instrument testing. The cool thing about the place here is, so we are engaged in instrument development that ultimately is beneficial to the deep earth as well. And we do field campaigns, and that actually involves seagoing research. And so just a few examples. Whoops. So the seagoing research, so here on the left side, you see an experiment where EM, so electromagnetic, magnetotelluric instruments were placed on the ocean bottom to answer a question if we can track where the volatiles in a subduction zone get subducted. And because the idea here is that you get the volatiles to a certain depth, and then that actually causes rocks to melt, and then eventually you get that up to the surface, and then you get the volcanism along subduction zones and at the surface. And so this research here on the left was an experiment done in Nicaragua, where the Cocos Plate goes underneath the still North American plate. And so so it's one of those poster child graphs, but then on the right side, there's something where I was involved, that I led, where we deployed a large number of ocean bottom seismometers around Hawaii to figure out how the Hawaiian plume really works. And the idea is that you have a vertical plume, and then when coming from deep inside the earth, and eventually pinches at the surface and then feeds the volcanism, the age progressive volcanism along Hawaii. But the reality is it's ways more complicated, where the plume is bending around and then eventually actually pinches into the upper mantle to the west of Hawaii and then comes up. Another example is actually, so in a geodynamics group, a very interesting question is, if you are a bit familiar with plate tectonics, of all the continents that we have at the moment, is the Indian subcontinent actually did a remarkably quick journey from the southern hemisphere in the last 60 million years all the way up then to slam into the Himalayas. And the question is, what was inside the earth that could facilitate such a fast journey? And so geodynamic modeling led by Dave Stegman reveals that so we have flat basalts in the western of India, and so that would suggest that you had a very productive plume there at the time, but that alone is not enough to explain that quick and vast journey. And so they figured out that you actually have a double subduction where the slab pulled and also pulled on the Indian subcontinent to make that travel faster and also over such a great distance. I actually skipped a slide, but that's okay. One thing that I really want to make a big deal out of is that, you know, the open house here is mostly conducted by folks at IGPP, but we have a geophysicist. We have geophysicists at the Geosciences Division as well. So the organization of Scripps is a little complicated. So that would be Jeff Gee. So he's a paleomagnetist. But we also work with non-geophysicists, so geochemistry, for example. And here are three of my colleagues, James Day, Pat Castillo, and Emily Chin, who analyze rocks and the minerals that are in the rocks and the volatiles that are captured in those rocks, to tell us something about Earth history and ultimately plate tectonics. And also, we also venture out to other planets as well. All right, my elevator pitch.
Thanks a lot, Gabi. That was awesome. Could you stop sharing screen, please?
Yes.
Thank you. We move on to geodesy and tectonics, and David Sandwell.
Morning, everyone. I'm Dave Sandwell, and I'm one of the older professors here. I shouldn't say old, I should say senior, not historic.
Historic.
But,
Dave, David, could you go into full screen mode, please? Thanks.
Yeah. And I'm here to talk about geodesy and tectonics. There's quite a lot going on in geodesy. There's the wrong slide. Let me go back. There we go. See the home pitch. Yeah. Okay, so I thought I'd start with seafloor geodesy because IGPP is actually the center for the instrumentation for seafloor geodesy. These are techniques that are used to measure the motion of the seafloor due to earthquakes and other processes. And of course, it's very hard to measure things on the seafloor because you can't put a GPS receiver down there. So there's two techniques that have mainly been developed here. One is GPS acoustics, where you use seafloor transponders and a wave glider. This is a picture of a wave glider being deployed just a week ago. And the wave glider hovers above, and they use that to locate the transponders, and you can measure horizontal motions on the seafloor. And then that is augmented with bottom pressure sensors, which are sensitive more to the vertical. And Mark Zumberg and Glenn Sasagawa are the main people doing this. Another major activity at IGPP is looking at all aspects of the earthquake cycle, interseismic, post-seismic, using a combination of GNSS and INSAR. And a lot of people around the world are doing this because there's really good data right now. We are really focused on California. You can see Yehuda Bach here, who's really installed a lot of the GNSS receivers around California and pioneered this effort. And then you see Yuri Fialko here, who is looking at mainly coast-seismic and post-seismic deformation, modeling that from very large earthquakes. Just 2 years ago or 3 years ago now, there were two major earthquakes in Ridgecrest, California, which is not too far away from here. These were very well imaged by radar interferometry, and you can see in the center here, these are all surface fractures from the earthquake, and you can see two major strands in the earthquake. One is running northwest, and one is running northeast. And this is a fun picture here. On the left is Ignacio and Eric and Jennifer Haas. This is the left lateral fault, and then on the right is the right lateral fault. So just a fun picture. Another new area of research relatively new at IGPP, and actually a new area of research, is hydrogeodesy. And this is the use of geodetic tools, INSAR and GPS, to monitor ground, mainly vertical ground deformation associated with the crustal fluids. This is a movie of crustal fluids filling up in the central California Valley, and you see Adrian Borza and his students and postdocs work on this on now. And on the right is Jennifer Haas. She does something very different. She uses GPS in aircraft and in balloons to monitor the water vapor in the atmosphere. And the upper panel here shows the balloons floating around the equatorial part of the Earth, and Jennifer's down below. I think this is in an aircraft setting up the GPS equipment. In our lab, we use satellite altimetry and shipboard soundings to investigate the remote areas of the deep oceans. And there's a number of people doing this, Yao Yu and Hugh Harper and Julie, and I'm down in the left here. And we continue to do this. There's a lot of really good data being collected, really improving our resolution of the oceans. And then finally, we have at least 2 GPS field trips every winter here when it gets cool in the desert. And here's some pictures from those field trips. We do these in collaboration with a group down in Sesese, Mexico. Sometimes we go across the border and monitor, look at the faults down in Mexico. And this is a lot of fun and a good way to learn how to use GPS equipment. So I'm going to stop there.
Thanks a lot. That was really great. Thank you very much. We dive into theoretical geophysics now with Dave May.
Okay. Hi, everyone. I am going to speak a little bit about what the people in the theoretical and computational geophysics group do. So sort of easiest, I think, to sit back or step back and think about, what it is, how do we learn about the Earth in general? And so the three sort of components, at least in our view of how we want to understand the Earth, is we have observations, we measure things, we have models, and we compute. Okay, and I draw a little line there just to sort of differentiate the topics that are sort of specific to the theoretical and computational geophysics group. We're mostly concerned with models and computation. And so the models that I have there are just some sort of partial differential equations that you might have seen that describe, displacement in a viscous or an elastic body, heat flow, or electromagnetism, things you may have come across before. And in the compute column, I have some examples of sort of high performance computing. So using a system like Expanse, which is located at UCSD, or low performance type computing that you might actually just run on your personal laptop. And so the sort of things that we model in general, this is not an exhaustive list, but there are certain examples here that I'd like to show you that I think might be interesting. We look at simulations and forward models of flow of liquid metals in the Earth's core. We look at and simulate cloud resolving atmospheric type simulations using large eddy simulations. We're interested in modeling fault slip and ground motion in complex media, sequences of earthquakes and aseismic slip over on the right, electromagnetism, and sort of large scale dynamics, simulations studying the dynamics of the lithosphere. And there's an example here shown of continental rifting. And in the scope of all of these types of models, there are lots of theoretical and technical challenges. For example, coupling different pieces of physics together, developing very efficient solvers that are and software that are able to simulate these processes in 3D and in space, and 4D if you consider time. So there are a lot of algorithmic challenges, mathematical challenges required to realize and enable the simulations that I'm showing here. And these are some of the topics that the people in the group work on. So we spoke a little bit about forward models. So these are in essence, the scenario where you have some model input P and you have some mapping F, which takes your model inputs and produces model output D. And ideally, you want to relate that to data, because our objective is always to understand how the natural Earth behaves. So we have our observations D and tilde, and we'd like to kind of connect them in some way, or at least understand how to make that difference between the model output and the data D small. And so one of the other major areas, activities or research activities that happens in the theoretical and computational geophysics group is to work on inverse problems, where you try and develop methodologies that relate D, the observations, to P, and constrain them in a way that that difference between the data and the model output is small. So solving inverse problems. And these are challenging for reasons, or mathematical reasons, and also there's a lot of computational reasons why solving large-scale inverse problems for complicated nonlinear multiphysics problems is challenging. So take a quick look at this sort of word cloud. There's a bunch of things I put in there. And what I want you to realize or take away from this slide is what we're doing in the group is geophysics, but much, much more, right? It's really highly interdisciplinary work. It spans applied math, computer science, data analytics. If these keywords and these word clouds are something that you find interesting, then you should definitely try and reach out to these people, which are the folks that are in the group. Welcome to contact any of us, discuss more about it, or you can contact me directly and I can point you to the person based on what your interests might be.
Thanks, Dave.
Thanks, everyone.
We move on to marine geophysics with Jeff G.
Good morning, everybody. My name is Jeff Gee, and I do some marine geophysics looking at magnetic anomalies. But as you've heard from a few other people, I'm actually in the geosciences group. So Vashon and I have sort of are two examples of people who do geophysics down the hill, but collaborate a lot with people at IGPP. So I'm going to show you just the three people on the left here are ones who have projects this year. So I'll highlight those and then end with a little plug for something Ross and I have going on. So there are, in addition to people in IGPP, there's marine geophysics more broadly, as I mentioned. So here's a collection of people who do that. And you've seen pictures of the ships before. So this is one thing that makes Scripps unique. So we have the two vessels on the left are the Revel and Sally Ride, which are global class ships, go anywhere in the world. And then the two on the right are vessels that work more locally. So one thing I would point out, there is a program for UC ship funds. So students can actually apply and sort of design and run their own cruises, which is a nice thing that you can do here at Scripps. So you've heard a little bit about the EM work. So Gabi highlighted some EM results having to do with melting. So EM, it turns out, is a really good technique to look at a variety of things. Here's an example of using it to map where you have methane hydrates on the seafloor. There's other work in this group that's gone to look at where you have fresh water stored, for example, on continental shelves. You heard a little bit about the seismology group. So I just wanted to highlight one of Wenyan's projects using seismic data, but with applications to the marine realm. So this is an example of some submarine landslides that were detected by using the US array, transportable array, and seeing that those were triggered. So landslides in the Gulf of Mexico were triggered by a 2009 earthquake that happened down in the Gulf of California. And then you'll hear a little more from Vashon. So just a picture of Vashon and some of his students in the Stripple, I think is how you pronounce that. So the Scripps Tectono Rock Physics Lab. So, but Vashon actually uses seismic techniques to look at neotectonics and how faults and rocks deform. And then I'll just end with a little plug. So this is a picture from one of the many cruises that Ross has had out looking at things on the ridge crest, the mid-ocean ridge. And in this case, looking at hydrothermal venting, but we have a project that will be going to sea hopefully in the middle of 2024 in a different place on the East Pacific Rise. Thanks.
Thanks a lot. Now we move on from the ships towards the next topic, one second, which will be polar science with Helen Fricker.
Hi, do you see my screen? Thanks.
Yes, and it looks perfect.
Great. I'm just going to give a very quick rundown of what we do in terms of understanding ice sheets and sea level rise at the Scripps Polar Center. So the PIs from IGPP that are most involved in this are myself and Jamin Greenbaum. And there's multiple other IGPP PIs who are involved in understanding Antarctica and Greenland in a sort of interdisciplinary sense. So at Scripps, we sort of focus on the ice shelves, which are the floating parts of the ice sheet. And this is a really great place to study because it means that we have to understand the atmosphere, the ocean, and the solid earth, and all these things come together. We know, and you probably have heard, that Antarctica is losing net mass, and so is Greenland. This video isn't going to play, but that's fine. I mean, the whole sort of big deal, the holy grail here is trying to understand how the ice sheet contribution to sea level, the sea level budget is changing. We know that it is increasing. And over the last 10 years, we've seen an increase in the amount of mass added from the ice sheets to the oceans. And that is affecting us here in San Diego and all around, wherever you are, as well in the coastal regions. So we are very interested in understanding the processes that are driving the changes. because the truth is our models are actually not particularly accurate of this, our ice sheet models. And so if we can go in and use some really nice combination of remote sensing and theoretical understanding of the processes driving the changes, then we will have a better chance at parameterizing those processes, putting them into our models, and getting improved, more accurate predictions on which society can make decisions for the future. Will you build an airport here? Will you build a building here? That kind of thing. So it's really societally relevant. And the reason why it fits in so nicely at Scripps is because actually it turns out the ocean is impacting the ice sheets, and understanding how the heat is being delivered from the ocean to the underside of the ice sheets is really important and involves multiple people in our institution. So I've had several students that have worked on sort of quite high profile papers related to this. This is Fernando Paulo. He looked at a very long time series of radar altimetry going back to the 90s, where he was able to show that the ice thickness on the ice shelves is changing, and that amount is increasing with time and adding to the ocean. And then he also managed to uncover some climate signals related to El Nino in those data, which was really nice. And helping us understand how the ice sheet is changing is also happening with a new instrument called ISAT-2, which many of us are working on. In IGPP, we also have a student working, Marnie Bryant, who's looking at permafrost applications to ISAT-2. So many of us are working across these instruments and these applications. Adrian Borsa is another PI who was mentioned earlier, who's looking at applications of ISAT-2 over different regions. And so this is another example of some students who've made some big contributions in this area from this program. So Jeremy Bass is on the left, using seismometers and GPS to show how rifts propagate in Antarctica. The rifts are important because they lead to these huge icebergs that get carved off the ice sheet. And Sushil Adesumili in the middle, who was able to use a long time series of data to extract basal melt rates on the underside of the ice shelves, where the water is actually being produced, the meltwater from the underside of the ice sheets to the ocean, which is a very pivotal paper a couple of years ago. And then on the right, Chloe Gustafson, who used EM, electromagnetic imaging or data collected on the ice sheet to actually infer a whole groundwater system under the ice streams, which was actually totally transformational. We didn't know that was there. So there are just some examples. And then just a little bit more going into other interdisciplinary areas. What's driving the snowfall on the ice sheet is very important. Atmospheric rivers that hit us here in California, the same mechanism is delivering huge amounts of snow and ice to Antarctica. And Sushil was able to extract the amount of precipitation that was added to the ice sheet by atmospheric rivers using the ISAT-2 instrument, which is, because it's a laser, it bounces off the top of the snowpack. And this is his melt rate work, which I already showed. We also have had some field work, and obviously this is very much impacted right now because of COVID and things, but we do have field work, and Jamin Greenbaum is about to go to Antarctica. I think he's leaving any minute. But this is a program, a historic program that's now ended, but this is on Ross Ice Shelf, just to show you the kinds of things that people do. This is Maya Becker, who is a student here in IGPP, and they were throwing an airborne float off the back of a plane and then into the ocean off the front of Ross Ice Shelf to get information about the ocean properties there. So yeah, I'm just going to finish with a couple of examples, things that we can do looking at processes by going in very detailed with this new information that we have from instruments that are very high spatial detail and good temporal coverage as well, to help us understand these processes that are driving the mass loss, which is going to help us in turn improve those models that I mentioned at the beginning. So it all sort of comes full circle. As we get better and better at looking at processes, we're able to understand what's going on the ice sheet. This is an example of looking at surface melt, because the laser on this instrument actually is able to penetrate through water, and we can get the depths of meltwater on the ice sheets, which is also pretty new and transformational. So here's our Polar Center. Here's me, here's Jamin, Fiamma Stranio, and then all these people. This is only a subset of people involved. If you go to this website here, polar.ucsd.edu, we do have a page on education. There's a page on PhD applications as well, and what to do if you're interested in Polar. And email me, and I'll try and point you in the right direction for information. So that's what I wanted to talk about. So thanks.
Thanks a lot, Helen. And we move on to the last pitch talk, which will be given by Vashan Wright about granular physics.
Hi, I'm Vashan Wright, and one of the relatively newer additions to the faculty. I do granular physics and tectonics, and it's innately interdisciplinary. And so we work with seismological tools, theory, etc. You can visit the lab to learn more about granular physics at www.lab.ucsd.edu. So granular media, which are particulate media within the earth, for example, and other places, it's vital to understand how it deforms, because the deformation of granular media is involved in a lot of the geohazards within the earth itself. That includes ice shelf collapse, glaciers, landslides, destabilized slopes, volcanic hazards, pyroclastic density currents, liquefaction, and it's vitally important for many of our climate change solutions. Despite the importance of granular media to many of these geohazards and things that are very relevant to people, we actually don't have a set of equations that adequately predict when granular material will flow, creep, or just catastrophically fail. And I like this cartoon by the New York Times, which says the era of difficulty of physics, sand and understanding granular media and coming to this set of equations is one of the most difficult. And that shouldn't dismay anyone, right? What it should do is inspire participation in this area, not only because of its importance, but it means there's many things that can be done in many areas for discovery when you think about granular material within the earth itself. I'm just going to highlight some of the things that we're doing now within the lab. One of the questions we're trying to answer is, how do granular media deformation sort of record past tectonic events within the earthquake cycle? That is, earthquakes, a seismic slip, creep, whatever. Or how does it exert control on earthquake nucleation? How does granular media deformation actually happen during the rupturing of the fault zone itself, which is quite important, because if you think about a fault zone, you can keep going in closer, and within that, there is some sort of gouge or crumpled up rock, and that's granular material. We do this in a variety of ways. We go into the field. These are examples of the 2 graduate students working with me in the field, looking at the fault zone within the San Andreas. We also do theory, numerical modeling. We do experiments within the lab. And we also are approaching this using statistical physics or statistical mechanics, which is kind of one of the revolutions in trying to understand granular material. We also think about, apart from fault zones, we think about how the internal and external stresses affect granular media deformation. And that could be, how do they deform in response to earthquakes, deform in response to us actually doing our geophysical surveys with seismic velocities, rainfall, or just how the contact forces are distributed within the granular material. And all of this particularly focused on landslides. And the other thing that we do to study these things is that we get the chance to go to these synchrotron facilities, and we shoot X-rays at sands. This is an example of shooting X-rays at sands, and we're able to then reconstruct them in 3 dimensions and look at all of the features of a granular material. And so I'm going to stop there and take it back to Alice.
Thanks, that was great, Vashan. We have a last scheduled item, that is the application process, and that will be presented by Venue and Fun. And we're running a little bit, surprisingly, a little bit short on time, but we have a very active Q&A session going on in the chat. So please keep the questions coming in there, and we're probably wrapping up after Venue Ann's explanation about the application process.
Okay. So the first most important thing is you have to submit your application before December 7th, 2022. And we do consider applications after the deadline, but we encourage folks to send in their materials early. And for this year, GRE scores are not required anymore, but they are optional. If you do plan to submit your scores, that is certainly welcomed. We spend a lot of time reading through your application materials, including your statement and also all the questions that you, all the answers to the questions in the application portal. So we encourage you to put in some efforts of addressing those questions and share your thoughts. Specifically, we focus on a few of the aspects in your statement, as well as the applications, but are not limited to related to your academic experience, which is your academic preparation, what you have done, or what scientific ideas that you have. We also value contributions to diversity, equity, and inclusion. To have a successful PhD, a good alignment with the program is important, so we can offer the resources that help you to achieve your goals. And to be successful, one more aspect is to be able to realistically evaluate your own strengths, as well as areas to be improved, and also longer term goals. So please try to put in some efforts addressing all those points in your statements as well as your application materials, other application materials. So a few words about how the review process is done. After the deadline, we will collect all the materials and review the materials as a curricular group. And then after that, some of the candidates will be invited for a Zoom interviews, hopefully in January, and we will start to send out offers in late January. But usually it depends on the schedule of the Zoom interviews, so they're not all at once. I think around mid-February, the SIO department will have an open house, and some of the applicants will be invited to attend the open house. After that is the time in between of making a decision and also sending out more offers, and the student decision deadline is around April 15. And so specifically, we actually only make recommendations of the admission to the SIO department, then the SIO department makes recommendations to the UCSD graduate division. So the process sometimes can take a little bit longer. PhDs are generally supported as research assistants in IGPP, but there are also some of the TA opportunities offered by the SIO department. We guarantee 5 years of funding for any PhD students admitted into the program. And the salaries are covering 12 months, a period of 12 months. We're hoping to have a more competitive stipend in regard to the current strike. Tuitions are covered, and as well as the health insurance. So if you have more questions about the admission process, please feel free to send me an email at gp-admission@ucsd.edu. I am aware there were some issues regarding this email address, but that has been fixed. And additionally, our student affair advisors might be here, and you can also directly contact them about the more general procedure regarding the application process.
Thanks a lot, Ben-Yuan. So I hope we covered a very broad overview of all the research that is going on and the support that is in place for our graduate students. And I hope you can also see by the amount of faculty that's in this virtual info session that we value our graduate students, and you will be able to work with really a large group of very diverse PIs with different expertise. And since we're already at the end of the hour, I encourage you with any further questions to reach out to gp-admission@ucsd.edu, and also check the recording that we will make available very quickly. And keep in mind the deadlines and get in contact with those folks that caught your interest during this info session. And thank you for taking the time and joining us today. And thanks for everyone of the faculty and to the student representative for contributing. Thanks a lot.
Thanks, everyone. Good to see you all.
Thanks, Elise.
Thank you, Elise, and everybody.